Okay. So what we were talking about last time, what we started last time was this idea of applications of integration, so integrals and context. When you have a word problem, how can we interpret it so that we understand what it's asking us to do is an integral? Okay. And an important point I also wanted to make last time, and I'm gonna hopefully continue to give you examples so you can see this, is that this sort of thing, this comes up everywhere in science. So like I said, math, physics, chemistry, biology, sociology. And if you can name 5 more sciences, it'll be used there too. This idea of differential equations. And as we've started to see, you solve a differential equation by doing some sort of integral or antiderivative. Now so far we've looked at sort of the most simple case. We're going to learn to do fancier antiderivatives, which will allow us to do fancier application problems. Okay. But so far, I just want to show you how it could apply in a couple different areas. So first, we looked at kinetics and physics with motion. Next, we look at economics. And now we'll look at some more examples as well. Okay. Electricity. All right. So what is electricity?
Movement of electrons.
It's the movement of electrons. Exactly. That's a great, short, precise definition of it.
I have a paper. If you want to read it right now.
Okay. Thanks for the offer. Okay. So how do we measure electricity? Well, if you just want to talk about a certain amount, you could just say you have a certain number of electrons. But as you could probably imagine, electrons are quite small, so we typically don't count electron by electron. So electrons all together, they form a charge. So you can talk about there being a certain charge on something. But as Costa said, electricity is the movement of electrons. So when you're talking about the movement of something, you're going to want to talk about how much of that there is per time. So how do we measure these things? Okay. So the charge, or the total amount of electrons, we'll usually measure in something called coulombs. And the letter that physicists use for that is Q. Why?
We use C.
I don't know.
Coulomb. That's what we use.
Oh, really?
Yeah.
Oh, okay.
But the variable we usually represent by Q, the unit
Oh, the
represents
unit.
C.
Yeah, that charge is
Yes.
Okay.
capital Q.
Yes, exactly. Okay. Physicists got my back. Excellent. Okay. So if you want to talk about how much, and when we talk about just electrons as a group, we don't say that group of electrons, we say that charge. Okay. That we measure in coulombs. And time we measure in seconds. And again, these are the standard physics units. And if you talk about electricity moving, the word for that is called the current. So most people have actually heard what a current was. Maybe you never thought about how to precisely define it in physics. Here you go. And that's measured in amps, which we represent by the letter I. Okay. So if you ever actually look on a circuit or a household appliance, it'll usually say how many amps it runs on. Well, now you know what that means. All right. So in notation, what this means is that amps is measured in coulombs per second, or in the really shorthand notation, I equals delta Q over delta T. Change in charge over the change in time. So this is the way that we think of rate when it applies to electricity. All right. So simple problem. Suppose at t equals 0 seconds, you have 4 coulombs, and at 4 seconds, you have 12 coulombs of charge accumulated, I don't know, in your hand, say, or somewhere more clever. All right, so what can you say about the current? What's the current?
Current is 12 minus 4 is 8. 8 over 4, which is 2.
So 12 minus 4 over
Over 4.
4 minus 0.
Yeah,
Okay.
I didn't ask it.
Well, you're too clever for me. Okay, I got to write the whole thing out. Okay. So the current is 2 amps. Now, of course, so what have we done? If you think just in terms of pure math, we took 2 points and calculated a slope. Okay. So also remember what that means. This means that what you're calculating is an average current. So we wouldn't necessarily know if it was exactly 2 amps the entire time. No? Okay. So now suppose the current is 3 amps. If you have 12 coulombs after 1 second, how many do you have after 5 seconds? So how do we do this? Sorry?
Delta Q is 4. Is 5 minus 1.
Delta
Well, it's gonna be
what?
Q final equals. I'll write it like that. I have to.
Okay.
Sorry.
So we're writing down some kind of equation. What's that going to be the equation? What's going to be the form of that equation?
Delta F minus QF minus Q initial
Okay.
over. First the current because we know it. Over TF minus T initial equal the current.
Equals. Right. Okay. So this is one. So and in this case, I know we've got some physicists because we're using physicist notation here. Final and initial. Okay. So mathematically, what is this a statement about? This is a statement about slope.
Yeah.
Okay. So this is really just the equation of a line. If you write it out properly. How can this be the equation of a line? Q. Well, okay, yeah. Q minus.
QF minus QI equal I times T. Okay. I times T is T minus T0.
Right. So normally we don't write Q. We write what letter? In math, what letter do we write? Y. And normally, and instead of T, what letter do we usually write? This is just the equation of a line. Okay. Now in this case, you get Q0 was 12, and I is the current, which is the slope, or the rate, and that was 3. T minus T0, we said we started at 1 second. So there's the equation of a line. And now, how do we solve this question? Plug in 5.
We also have the T final.
Yes, but to make it more transparent, what we actually have here
Q of T.
is Q of T. It's a function. And now we can plug in 5. Now, you can plug in any value. This problem's asking you to plug in 5.
So any of the physics formulas that have like a definition of a variable equals delta variable over delta variable is basically the slope is equal y change in y over change in x, basically.
Yep.
I can visually imagine pretty much any kind of formula right off the bat.
Yep.
If we have this question, for example, on the test,
Yeah.
you want to do all this, like, you can't do it. You have to do it like this function of t and then you block.
Oh, you can. So there are a lot of different ways to write this problem. I mean, how many ways do we know how to solve like some kind of linear type problem? You know about 10 different ways. But I wrote it like this for a reason, because I want to ask now, how is this calculus? Well, the equation that I just wrote down should look familiar not just from algebra, but also from what we've talked about, how this becomes calculus. So how does this become calculus? Suppose the current varies. Oh, too far. Seriously? All right. Okay. So at time t, the current is I equals 1 plus t. How much charge is collected between 2 seconds and 5 seconds? And by charge collected, I mean what's the total change in charge? Well, you can't use the equation of a line. Why can't you use the equation of a line?
That tells you a specific point.
It's not linear.
It's not linear. The slope is changing, or the rate is changing. And when the rate is changing, we have to use calculus. So, how can we use calculus here? Sorry? Okay. Right. So here's the current, and we're going to take the antiderivative of that. And now, generally speaking, if you take the antiderivative of the current, what do you get? Oh, yeah, you get the original function. What is the original function when we're talking about electricity?
Slope, you mean?
Okay. So there's an original function, and then there's a derivative of it, which is the slope. So what's what in this problem? I is the slope, because what did I represent? Yeah, I represented the rate of change for something. What was that something? The charge. Exactly. So electricity problem. So we can think of these electricity problems as about total charge or amount of charge and rate of change of charge. So I is the current. That's the rate of change of the charge. Take the antiderivative. You're going to get the amount of charge. So that's the general idea. Now we can specifically use the fundamental theorem of calculus.
If we move the t, what do you get?
Because what we want is what is the total change in charge between t equals 2 and t equals 5. So how can we use the fundamental theorem of calculus to set that up?
The integral of the function, and then you put the boundary, the time.
Right. So integrating the current from 2 to 5 is the same as simply saying I'm taking the integral of the derivative of q. In other words, the derivative of the amount of charge. And what's that going to be? That's going to be, by the fundamental theorem of calculus, q of 5 minus q of 2. But q of 5 minus q of 2 is the change in the amount of charge. And now we can work that out. Okay, so we need to integrate. So this is the integral from 2 to 5 of one plus t dt, and that is t plus t squared over 2 from 2 to 5. So that is 5 plus 5 squared over 2 minus 2 plus 2 squared over 2. And that just works out to be, what? 17.5. 13.5. Okay. By the way, 13.5 what? What are we measuring? Exactly, we're measuring charge, so coulombs. Okay. So, some people previously asked me, can't we just use the plus C method? That fundamental thermic calculus looks kind of confusing. And I said, well, yeah, but there are some times when you're going to have to use the fundamental thermic calculus. This is one of those times. Because that constant, that plus C, it's not really there because what you're interested in is the Q of 5 minus the Q of 2, and that's the thing you're actually trying to solve for. So there's no plus C here. You need to actually find the change in two function values. And that's exactly what integrating f prime does, or in this case, integrating q prime.
But I just don't understand, like mathematically, how do you get from that equation to that equation where the t disappear? I understand that the t is the span,
Right.
but mathematically, what happens to it?
Okay. So.
Because that would be I equals
Right.
dq over d.
So this is. Let's see. Q of 5. Well, okay. So here I said 1 second. So Q5 minus Q of 1 equals the derivative times T2 minus T1. Okay. And now I'm going to say Q5 equals Q1 plus, well, M, what was M?
Was
Right. Right, so M is the same as I, but I is Q prime. You know what?
why is q? That's what I can't understand. Why
Okay.
would it be just q prime? Because
Okay, so sorry. Actually, first let me finish the follow-up question, and then I'm going to answer your question in detail. So hold on 1 second. So back to this question. Follow-up. If there are 4 coulombs at t equals 2 seconds, how many coulombs are there at t equals 5 seconds? Yeah, I'm continuing the same problem. Right? So what did we just figure out in the previous problem? The change was 13.5. So
So it's 9, it's 8.5.
So
Oh, it's plus 17.
17.5 what? That's right. Okay. So this is one of the harder aspects of using integration, is to understand how this works in applied problems. And you have to understand, it's helpful to understand the relationship, again, between which function represents your amount function and what represents your rate function. So in this case, we're starting at the rate function, because current is a rate, and then we're taking the antiderivative to get back to the amount function. Okay. So how could we use calculus to do the previous problem? So first I'm going to talk about it that way to answer that previous question. So we could say that the current is 3 amps. Okay, so the integral of 3, so let's see, so we know that Q equals the integral of Q prime. So we're just going to integrate 3 dt. So we know that Q actually equals 3t plus c. Well, okay, but we also know that at 1 second you have 12 coulombs. So Q of 1 is 12, which is 3 times 1 plus c. And now you can see that c must be 9. So what we know is that Q of t has to be 3t plus 9. And now you just plug in 5.
I understood that. No,
Okay. So that would be doing it using the plus c method. You could also do it using by the fundamental theorem of calculus approach. So that is solving the previous problem, which was quote unquote simple because it's linear, using calculus. Now let's go the other way. How would you take this approach and walk it forward so that it becomes calculus? Well, remember how we learned what an integral was. We said, well, okay, so I'm going to go back to, I'm just going to copy over this piece right here, but I'm going to copy it on the bottom. Q of 1. What do we say? Oh, 3. Okay. So how do we turn this into calculus? Well, remember what we did. We said that the original function is some initial value plus q prime at that, and by initial value I mean initial x value. Initial x value and t minus 1. But then we said this is just a linear function. What if we want to get, assuming the rate we're changing, we'd want to make a better approximation. How do we make a better approximation? We add in more of these q prime terms. So we could say this is really q1 plus, let's say, q prime of 1, I don't know, 1.5 minus 1 plus q prime of 1.5 times 2 minus 1.5 plus blah, blah, blah. And we had to do that when the slope or the rate was changing, which is about when making the transition from linear functions to nonlinear functions and from just algebra into calculus. That's what that's about. So that's why the approach of thinking of it as a linear function, when you move to nonlinear functions, you suddenly have to do integration. Of course, what I've written here is an approximation, but as we know, this approximation, if you want to make it exact, you do an antiderivative.
For another approach on answering the previous question, could you just take the indefinite integral of that so that it would give you the original?
Sorry, which one? Where the current is 3 or the current is 1 plus t?
Yeah, 1 plus t.
Okay.
What if you just take the indefinite integral of that and evaluate it and just plug in the points? Because if you took the integral of that, you would get qt.
I'm trying
just plug in.
Okay. So that's a great question. So can you do that? So we know that q is going to be the integral from 2 to 5 of I dt. So this is just integral from 2 to 5 of 1 plus t dt. And this is, oh wait, I'm sorry, you said indefinite integral. Sorry. Right. Okay. It's indefinite, so q, so you get,
It would be the change in Q, right?
hold on. Well, he's talking about using the indefinite integral, so just finding the general antiderivative. So we know that q equals t plus t squared over 2 plus c. Okay, so now what?
Plug in those, like plug in q of 5. And just, if you have the original function, you
Okay.
just plug in the needed point of q of 5 is 5 plus 5 squared over 2. And then-
Okay.
And then you would subtract q2, and then the c's will cancel out.
Absolutely. Don't have enough room here quite. Sorry. And the c's will cancel, and we're getting the exact same thing. So you can do it that way. You're absolutely right. So the way Paul did it was he used a slightly different notation, but notice that he's basically doing the exact same thing. You say, you find the antiderivative, then you find what it is at 5, you find what it is at 2, and you take the difference. But you know what? That's exactly what the fundamental theorem of calculus says. Fundamental theorem of calculus says, take the antiderivative, evaluate it at 5, evaluate it at 2, and take the difference. And that is q of 5 minus q of 2. So you just rediscovered the fundamental theorem of calculus.
But like on the follow-up question, can you just plug in q of 5 with ignoring the initial condition? Because you have the original function. Like, can you just ignore it if there are 4 coulombs at 2 seconds? Can you just directly plug in q of 5?
Ah, okay, good question. Can you do that? Well, plus c. You need to know, in order to figure out the actual amount at t equals 5, you need the actual amount at some other point in time. Does that make sense? Okay.
Should be, it's like so basically change in q is going to be equal to the antiderivative of I from the stem. Okay.
Yeah, that's exactly what it is. So to sum up, if it's just linear, the change in q looks like this linear function. But if things aren't linear, you can't just take the slope times delta t. You need to perform an integral. And that's what Calc 2 is all about. Okay. Let's see. All right. So let me give you one to do. Okay. 2. Okay. So I'll do that one. Okay, so how does this go?
17 plus 95, which is fine.
Okay, how do you do it?
Take the integral from 0 to pi on the function.
Okay. And if you do that, what is that going to give you?
Delta
3x
I mean, theoretically speaking, doing the integral from 0 to pi of the function for the current, what does that tell you?
area under the curve from 0 to pi.
Okay. And in this case, we interpret that as meaning what?
delta Q T.
This is the change in the charge. So you're exactly right. You could think of this as delta Q. In this case, that just means Q of pi minus Q. Ran out of room. Minus Q of 0. Okay. So it's the integral from 0 to pi of cosine t plus 1 plus 3t dt. And that gives you what?
Sine t plus t, 3t squared.
From 0 to pi. Okay.
Or 0 is 0.
Okay. So you get sine pi plus pi squared over 2 minus,
Isn't it 3?
right.
Next to the pi squared.
Sure. Yeah.
Minus
0, 0, 0. Okay. So you get pi plus 3 pi squared over 2, and you guys are telling me that that's approximately 17.9. 17.9 what?
9.5.
Oh, 9.5. Oh.
9.45, but 9.5.
Yeah.
Oh,
About 17.9 coulomb. I'm sorry? You got negative 17. Okay, so why did that happen?
or minus sign.
He switched, maybe he switched 0 and pi.
Okay.
Maybe just switch the derivative and then.
So we got two guesses.
You know why?
One person suggesting maybe you did the derivative instead of the integral. Is that what happened?
He started with a 0.
Yeah.
And then
Okay.
minus pi.
Did you start with 0 and then subtract off with pi? That's what happened. There you go. So the way to set it up and write it down properly is the way that we've done here. So when we say going from 0 to pi, you write 0. You write 0 as the bottom boundary at the integral, and then pi as the top. Yeah. Hold on. All right. Right. So 0 goes on the bottom, and then pi goes on top. And then when you do the calculation, you do the pi 1 minus the 0, 1. And again, just to go back to the linear case, in the calculation, this is exactly the same as y2 minus y1. Okay, so does that make some sense? Okay.
Would it be milk wrong if we didn't find the 17.9? Stop that with equals.
Oh, right. Good question. you were to leave it as pi plus 3 pi squared over 2, mathematically that's correct. But I always like to, so that would be correct, as long as you put coulombs. However, as a person imagining that this is like an applied situation, you'd probably want to know about how much charge that is. So personally, I like to put it's about 17.9. You don't have to, but I just find it helpful because it reminds me of what I actually have in my hands.